So in today's video, I want to talk about some recent results that I've proven in some recent papers regarding the Schwarz Lemma. So this is based on the recent work which is available on the archive. The paper is the Schwarz Lemma in Kähler and non-Kähler geometry, and the notes, which are expository and are built from this lecture material, is all to be found in the paper which will appear very shortly, which is the Schwarz Lemma and Odyssey. So the Schwarz Lemma is one of the pioneering results of the function theory of a single complex variable. It says that if we take a holomorphic map between disks, let's say the first disk has radius r1 and the second disk has radius r2, and for simplicity we'll assume they're both centered at the origin, then any such holomorphic map between these disks which fixes the origin satisfies the inequality that the modulus of f is bounded by a ratio of the radii times the modulus of z. This is an inequality that everyone learns in the subject and was proven by Schwarz more than a century ago. So if we keep R2 fixed and let R1 get arbitrarily large, so the disk in the source domain of the function f, if that is allowed to get arbitrarily large, then we recover the following well-known corollary, namely Liouville's theorem, which states that a bounded holomorphic function, which is holomorphic on the entire complex plane, assumes at most one value. In other words, the function is constant. Now, just to give everyone some motivation on why you would care about such a theorem, let's just note that the fundamental theorem of algebra is a theorem precisely of this nature. Namely, a non-constant algebraic function, which is defined on the entire complex plane, assumes all finite values. So in a sense, it's actually the opposite of a Schwarz-type theorem. So if the polynomial is non-constant, it admits at most one value in the Riemann sphere, or admits no values in the complex plane. So the Schwarz lemma is a local finite statement about holomorphic maps, while in contrast the Liouville theorem is a global statement which we obtain from limiting the Schwarz lemma in a sense. Namely that we let this R1 tend towards infinity, and in that case we ended up with the Liouville theorem. Now this is a prototypical example of a more general heuristic, which is referred to as the Bloch principle. Namely that any global statement concerning holomorphic maps arises from a stronger, finite version of the statement. So the Liouville theorem, which even though we may discover first, comes from the Schwarz lemma sooner or later. There is a finite, stronger analog of a global theorem regarding holomorphic maps. This is the quote from Bloch's 1925 paper, which says that nothing in the infinite cannot come from the finite. Everything in the infinite comes from the finite. So to give another instance of Bloch's principle, let us note that the Liouville theorem is generalized to the Picard theorem, which states that if we look at a non-constant entire function, so a holomorphic function which is holomorphic on the entire complex plane, then that assumes all but possibly one value. So this is very, very analogous to the fundamental theorem of algebra regarding algebraic functions, but of course entire functions are more general. Now, what is the finite analog of the Picard theorem? The Picard theorem is a global statement about holomorphic functions. The underlying finite statement is what's referred to as the Schottky theorem, which says that if we take a holomorphic map from the disk to the complex plane, such that it omits the values 0 and 1 in its image, then we can bound the modulus of f in terms of the absolute value of z and the value at the origin. Now, it's worth pointing out that the original proof of the Schottky theorem gave, in fact, no explicit bound. The bound is implicit. So the first instance of the Bloch theorem, or the Bloch principle, I should say, is the following case. So if we look at the Valeron theorem, which states that a non-constant entire function has holomorphic branches of the inverse in arbitrarily large Euclidean disks. What this means is if we look at a point where the derivative vanishes, that would be the limit of one of these Euclidean disks, and what we say is there are no branch points in this case. Now, what is the corresponding finite version here? Well, the finite version is that every holomorphic map in the unit disk has an inverse branch in some Euclidean disk of radius delta times the absolute value of the absolute value of the derivative of f at the origin. And moreover, this delta is in fact independent of the map itself. It's a universal constant that is true for all holomorphic maps. So this theorem of André Bloch and this Bloch principle, it's worth noting, Bloch was a mathematician in the early 20th century, and he has a rather interesting life. It was 1917 when he invited his family over to a dinner. He had a dinner with his aunt, his uncle, and his brother George, and there was a history of mental illness within his family. On his mother's side, they had a history of mental illness, and because of this, André Bloch believed that it had to be eradicated from the bloodline. It was a eugenics act, and what he ended up doing is murdering his family, murdering his uncle, his brother, and his aunt. And after stabbing them to death, he ran out into the streets and he was arrested. He didn't resist arrest, but he spent the rest of his life in a psychiatric ward. And you can read the description from his psychiatrist, where he would there was a table outside his door, and he would just come out every day and do mathematics at this desk and look out the window. There was a window near this desk, and he would just do his mathematics. And he ended up doing he proved the Bloch theorem, which extended the theorem of Valeron, and this is quite a significant achievement in the subject of one complex variable. And he in fact collaborated with many great mathematicians, including Hadamard, Mittag-Leffler, Poincare, and Henri Cartan. And if you can read some discourses of Mordell, where he's speaking with Hadamard about how he met André Bloch, and of course all of these collaborations would have occurred via correspondence, and of course when you have these correspondences, you put your address down, and he would put down the address of the psychiatric ward, but he wouldn't indicate that it was a psychiatric hospital. And most of the mathematicians he corresponded with had no idea of what was actually at this address. And it wasn't until Hadamard was in France, where André Bloch was, and said that, I'm close by, you should come visit. And Bloch responded something to the effect of, due to certain predicaments, I'm unable to come to you, but you're more than welcome to come see me. And it was only then that they realized that this man had been proving all these great theorems from within the confines of a psychiatric ward. I mean, of course, Ted Kaczynski is another instance of this type of phenomenon, but he didn't keep proving theorems after his non-mathematical endeavors. Okay, so one thing I hope to convey here is the certain divide that exists within the literature concerning the Schwarz Lemma, and that this divide should be noticed, and in fact what has led to the recent developments is making use of the third aspect of this division, which has been long neglected, or has been believed to be superseded by further developments. So this first part we'll be talking about the PIC Schwarz Lemma. As it stands, just to remind ourselves, the Schwarz Lemma controls the growth, or maybe a better word would be distortion, of holomorphic functions. So it says that they can't grow too much. If I have a holomorphic map from the disk of radius r1 to the disk of radius r2 and it fixes the origin, then the disk in the image that it maps to cannot be larger in radius than the ratio of the image disk divided by the ratio of the source disk. Now, it was observed, this is an old theorem, this is shortly after Riemann's attempt at the proof of the Riemann mapping theorem, and which was around the mid 19th century. And it was observed by Pick in 1916 that the Schwarz Lemma could be given a radically different interpretation. The first thing to observe that was observed by Pick was the assumption that f of 0 is 0 itself, so it fixes the origin, was actually unnecessary to assume. Suppose that f maps the origin to some non-zero point in the disk, then what we can do is we can use a Mobius transformation, which is given here, or a fractional linear transformation, to essentially put that image back. So if I have a point alpha in the unit disk, I can map it back to the origin exactly by this map. So now I can use the homogeneous structure of the disk to construct a holomorphic self-map of the unit disk which fixes the origin. Namely, I send f to the disk, which sends the point 0 to the point alpha, and then I use the fractional linear transformation or the Mobius transformation to send alpha back to the origin, and then consider the composition. Now, if I apply the familiar Schwarz Lemma in this case, what I end up with is the following inequality. Noting here that f of, I've been a little more general here. I've said that it maps w to f of w instead of assuming that f of 0 is 0. So now we can define this function, this function that appears on the right-hand side of that inequality. We'll call this the pseudo-hyperbolic distance, and that's a reasonable name because this does indeed define a distance function. Namely, it's a symmetric non-degenerate function and satisfies the triangle inequality. But in a sense that will be made clear in further developments and is important in the sense that Pick did not give his theorem in terms of the pseudo-hyperbolic distance. We want another distance function. We're going to want a distance function that comes from integrating a Riemannian metric. So this one does not come from an infinitesimal structure. It comes from exactly this formula here. There's nothing intrinsic or infinitesimal about it, I should say. So how do you get a metric from integrating or how do you get a distance function from integrating a Riemannian metric? Well, we know how to do this in the case of curves. If we take a curve and I look at all the tangent vectors, what I then do is I look at, I zoom in and I take this triangle here, this infinitesimal triangle, and I add them up. That will give me, essentially what I've done is I've added up all the tangent vectors to this curve, and that tells me the arc length. So the distance between any two points on the curve is exactly given by this integral expression here. Now, if we're on a manifold, then we can definitely do the same thing, because a Riemannian metric is a symmetric non-degenerate bilinear form on each of these tangent spaces. So we have an inner product on each of these tangent spaces. And what we can then do is, as the curve is moving along the manifold, we have a tangent vector along each point, supposing it's a smooth curve, and then we can basically calculate the norm of each of these tangent vectors at each of these tangents in each of these tangent spaces using the Riemannian metric, and then add them up as we integrate along the manifold. So that will give us a distance function if we have an inner product in each of these tangent spaces which varies smoothly. So one instance of a Riemannian metric on the disk which is very natural to consider is the Poincare metric. So the Poincare metric is given by the arc length element, which you can think of a dz tensor dz, or actually more precisely dz tensor dz bar, divided by 1 minus mod z squared all squared. Now, just to get some intuition for how the geometry changes when we endow the disk with the Poincare metric as opposed to the Euclidean metric, let us compute the length of a line segment which connects the origin to some real number w, which is between 0 and 1. So what we see is that if we can parameterize the curve gamma, this arc length element or this line element by a curve gamma, and gamma will of course just be defined by t times w, then the length of this is just given by integrating over L of exactly the Riemannian metric element. Now, what we see from the formula for rho is that we'll end up with w over 1 minus w squared t squared, and then we can express that by rearranging appropriately as the integral from 0 to w of dt divided by 1 minus t squared. And then elementary calculus will then tell you that this is exactly 1/2 of the logarithm of 1 plus w over 1 minus w. Now from here we can consider an associated distance function, namely the distance with respect to this. You can show that the distance function for the Poincare metric is given by 1/2 of the logarithm of the modulus of this fractional linear transformation. Now what do we see here? What we see is that the shortest length between these curves is going to be given, so that the thing that minimizes the length functional, at least locally, will be given by arcs which emanate from the boundary of the disk. So they will take an infinite amount of time to get to the boundary of the disk. So in particular, it's a complete metric. We'll have these arcs which are orthogonal to the boundary of the disk, and those paths are the ones that are the shortest distance with respect to the Poincare metric. So in fact, the geometry is very different. It's a very different to Euclidean geometry here. We have a tendency to diverge as opposed to remain parallel, for instance. So if we summarize this discussion, what we've essentially done is recovered the following theorem of Pick, which is referred to as the Pick-Schwarz Lemma. Namely, that if we take a holomorphic map from the unit disk to itself, I'm just going to assume the radius is 1, which does not necessarily fix the origin this time, then the inequality we proved before using the fractional linear transformations says that the distance function with respect to the Poincare metric decreases under holomorphic maps. So all holomorphic maps are distance decreasing with respect to the Poincare metric. Now, this has some important consequences, because what we see now is that the content of the Schwarz lemma is not actually about holomorphic maps. It's about the distance function. It's about the distance function associated to the Poincare metric. So that's the sense in which we want to think of this as a rift, as a divergence in the developments. So one thing I should definitely do is not just tell you old things. I should tell you, some things that have occurred more recently, let's say, although these are still old results. And this is the subject of intrinsic metrics on complex manifolds. So the Poincare metric has the property that it is invariant under the automorphism group, namely the fractional linear transformations are isometries, and all holomorphic maps by the Schwarz-Pick theorem are distance decreasing with respect to the distance function associated to the Poincare metric. And it's natural to ask whether there is only one such distance function that has this property. And it turns out that there are actually a large number of such structures, namely the Carathéodory pseudo-distance function, which we can define on any subdomain of Euclidean space, is given by the supremum of the distance function associated to the Poincare metric of the image of those 2 points under a holomorphic map. So what we do is we take 2 points in our domain, we map them via a holomorphic map into the disk, and then we compute the Poincare distance in the image, and then we take the supremum of this quantity over all such holomorphic maps. Now, this is going to be invariant. It's known that this is invariant under the automorphism group of omega. and moreover is distance decreasing, of course, with respect to holomorphic maps. Now, it's a pseudo-distance function instead of an honest distance function because it can be degenerate. It can, if omega was allowed to be compact, for instance, then all holomorphic functions would be constant, and therefore it would just annihilate everything. Distance between any 2 points would be 0. But this is an instance of what's referred to as an intrinsic pseudo-distance. Now, of course, one would like this on all complex manifolds, and one can do this. In fact, the most natural candidate is something called the Kobayashi pseudo-distance, which essentially what we do is we take any sequence of points which converge to the corresponding points we consider here. So I have a sequence of points converging to maybe a point Z and another point W in the disk. What we then do is map these in a corresponding way. So we have this chain of holomorphic maps, and then we compute the sum of the Poincare distances between each of these points in the sequence, and then take the infimum of that over all such chains of holomorphic maps. The definition is unfortunately convoluted, and so I figured that a diagram is more than sufficient to at least discuss the idea. Okay, so we now want to talk about the second divide, which is due to Ahlfors. So Schwarz told us that the Schwarz Lemma was essentially a statement about holomorphic maps, so the distortions of holomorphic map. You know, the image of the unit disk with respect, the radius of the image of the unit disk is bounded by the ratio of the constituent radii in the domain, and it should be R2 over R1, I think. While the PIC Schwarz Lemma says that no, it's not that the holomorphic map is the object of study. It's the Poincare distance function that is the object of study here. So this led to obviously some great developments, but it was actually really the observation of Ahlfors that really shot the Schwarz Lemma into what it is today. And in fact, those intrinsic distances would not have arisen if it wasn't for this result here. That's more of a fact about history than it is about mathematics, though. So what we're going to have to do is we're going to have to talk about the fact that the Poincare metric came from a Riemannian metric. Now, a Riemannian metric allows us to talk about intrinsic properties of a manifold, and in particular a surface. So one of the most important features of the metric is its curvature. So how a space is curved when it is endowed with a certain infinitesimal length element, namely the metric. So what we have here is we have this surface, a Riemannian manifold of dimension 2. And let's look at the point in the middle of this saddle. And what we can do is we can look at its unit normal vector. Its normal vector in the direction. So it's normal vector when it is realized as a surface inside of R3, which is obviously what we're doing here. Now I can look at the tangent plane at this point as well. And I can now look at the parabolas which are formed from this surface. So here I have these parabolic graphs that are realized over the tangent space and within the normal plane. So these are called the planes of principal curvatures. And now I could fit a circle in here that will touch this point up to order 2, up to 2 derivatives it will coincide. And the reciprocal of the radius of that circle will be the principal curvature. And so what I can then do is look at the product of the principal curvatures here. And it's obviously you have to take some orientation into account. Here we're going to have when we have this standard parabolic thing, it's bent in here while it's bent out here. So we'll have some positive curvature in this direction while negative curvature in that direction. And then what we do is we say that the curvature at this point is the product of the principal curvatures. So here, because we have a negative and a negative and a positive, we will have negative Gauss curvature at this point. Now, this is obviously a terrible way to do things because it entirely relies on the extrinsic nature of things, at least in the way I described it. And we have this formula here which says that if we take the lambda here is the coefficient in front of the arc length element, the coefficient in front of the mod dz, then the Gauss curvature is given by essentially the second derivative or minus the second derivative of the log of that function. And then there's this normalizing constant. Well, you normalize it by the metric itself. So just to get a feel for the various types of curvatures, if we have the sphere is positively curved, so it's bent out everywhere, that's a nice way to think about it. Vanishing curvature is what we see on the plane. The torus also has vanishing curvature. And negative curvature is when we're bent in, hyperbolic. If we look at a high genus surface, so a surface of genus G greater than or equal to 2, then this is also an example of a surface which admits negatively curved metrics. So these, you can put a metric if in fact constant negative Gauss curvature on these things. Of course, they look bent out somewhere, but that's because of that's not intrinsic, that's extrinsic. That's how they look when you embed them in a Euclidean space. So the point, just to illustrate these ideas, because it may seem complicated, but it actually is quite elementary. If we have the Poincare metric, which is given by this formula here, then the lambda here is given by 1 over 1 minus mod z squared all squared. And what we want to do is compute the Gauss curvature here. So we need to take the log and compute its second derivative, or its complex Hessian, put a minus sign, divide by the metric. So what we see here is actually that you'll end up with, when you do this calculation, is exactly minus 1 over the coefficient of, when you compute this, you will end up with 1 over 1 minus mod z squared all squared. That will give you a minus of 1 minus mod z squared all squared divided by itself. And this will be simply equal to minus 1. So it'll be independent of the point. And so in particular, we see that the Gauss curvature of the Poincare metric is constant and equal to minus 1. So it's constant and negative. Now, it's the theorem of Ahlfors that this is precisely what the Schwarz Lemma is about. Namely, he says that if you get a Riemann surface, or a one-dimensional complex manifold, so imagine a two-dimensional surface, like a sphere, like the Riemann sphere, and it has a complex structure, so it's a complex manifold, it locally looks like Euclidean space with respect to holomorphic charts. You have a local holomorphic coordinate system in every point. And you have a metric on there of Gauss curvature, which is less than or equal to minus 1. The precise value is just a normalizing factor. You can, as long as it's negative. Then any holomorphic map from the disk into this space is distance decreasing in this way. Namely, if you take the distance function with respect to this metric of negative curvature, then it does not increase relative to the Poincare distance. So you have this image from the disk between 2 points, and what will happen is that when you map it in, there will be a contraction. Of course, this is not to do with Euclidean distance, it's the hyperbolic distance, so the picture can only say so much. So here we see this threefold rift or division. The original formulation by Schwarz is that a holomorphic map is constrained in the extent to which it can be distorted. Pick says no, it's not the holomorphic map that's the content, it's the distance function, it's the distance with respect to the Poincare metric. It's the fact that holomorphic maps are distance decreasing with respect to this thing. So you don't want to study the maps, you want to study the metrics. But then Ahlfors then says, no, it's not even that. It's the fact that there's negative curvature underlying the metric associated with this distance function. And in this way that we see this lineage, this supersedence of each of these developments, and that's often how it's portrayed. But what I would prefer to argue is that these are just three perspectives. Of course, the theory of dilations of holomorphic maps, people study that when they look at often boundary behavior of holomorphic maps. They think about it in this way. People who study Kobayashi hyperbolicity and things of this nature, these intrinsic pseudo distances, they view the Poincare distance as the way to view things. And within Kähler geometry and these differential geometry, the differential geometry of complex manifolds, we really view curvature as the object of study here. And the map is somewhat irrelevant, the distance is irrelevant, it's really the tensor calculations that we care about. Now, it's worth noting that in Ahlfors' collected works, you find the following reflection of Ahlfors concerning his Schwarz Lemma, which has been a tremendously important development. He says, he confesses that it had more substance than I was aware of. But without applications, my lemma would have been too lightweight for publication. Now, what applications is he referring to? Well, the first one is that he was able to give a proof of Schottky's theorem, which we stated earlier, but was actually able to give a definite numerical bound on it. Now, recall before that it was an implicit bound that was obtained by Schottky. And here we have that if f is a holomorphic map from the disk into the complex plane, such that it omits the values 0 and 1, then the log of its absolute value is bounded by some constant theta, which is less than 1. And then we have a bound exactly here, 7 plus log of the absolute value of f is 0. That's already a remarkable achievement, but he in fact gave a substantially improved bound on the Bloch constant. So the Bloch constant was that constant we discussed before, and it was this primary motivator that gave us this version of the Schwarz Lemma. So it's interesting. You have all these developments which are kind of in the background there. They're fueled by this Bloch constant discovery. People trying to discover this constant associated to holomorphic functions. Now, let's just recall the statement of the Bloch theorem, namely that every holomorphic map in the unit disk has inverses in the inverse branch in some Euclidean disk of radius delta. So let's just recall the statement of the Bloch theorem, namely that every holomorphic function in the unit disk has an inverse branch in some Euclidean disk of radius delta times the absolute value of f prime of 0, and delta is this absolute constant, which we now call the Bloch constant. So Bloch was able to show that this thing was bounded below by about 1 on 12, or was bounded below by 1 on 12. And Ahlfors was able to show that it was bounded below by root 3 on 4. And Ahlfors and Grunsky were able to show that it's bounded above by gamma of 1/3 times gamma of 11 over 12 divided by square root of 1 plus root 3 times gamma of 1/4, which is about 0.4719. So it's in fact conjectured that this ratio of gamma functions is the bound. So we know that it's actually bounded above by, but it's conjectured to always be the case. And so what remains is to get a sharper lower bound. And at present, the current record is held by Xiong in 2004. He was able to show that the Bloch constant is bounded below by root 3 on 4 plus 3 times 10 to the 4, which is about 0.4333. And what's kind of fascinating is that it remains unknown to this day as to what the precise value is. It's an unsolved problem, and it's almost like, not knowing what pi is. It would be, I'm surprised that people aren't just hunting for it as much as I imagine they'd be hunting if we didn't know what pi was. So each of these, as I attempted to elucidate, each of these formulations have led to huge developments. The Pick-Schwarz lemma has led to the notion of Kobayashi hyperbolicity and the study of these intrinsic metrics on complex manifolds. The Ahlfors Schwarz Lemma has led to important developments in second-order estimates in Kähler geometry. Things like the Calabi-Yau theorem fundamentally rely on the subsequent developments of the Ahlfors Schwarz Lemma. And generalizing the original formulation has often been done with a focus on the boundary. But the developments that actually, so the original formulation, so I was able to prove a vast number of Schwarz lemmas, which are in the spirit of this Ahlfors Schwarz lemma, but the idea is to actually focus on the holomorphic map. So you realize that certain curvature terms arise because of certain underlying holomorphic maps. And with that in mind, what you can do is construct certain results by attempting to construct the associated holomorphic map. So if I want to bound on one curvature, and I know that always arises in the image of a holomorphic map, then I know to construct a certain map that has that image using composites and so on. And that actually turned out to be extremely fruitful. Yeah, so it's definitely not the case that each of these has superseded the other. They are three different perspectives on the same thing. And what I'm attempting to argue here, and unfortunately want to argue further, but is a little more technical, is that the holomorphic map is the object of focus, not the metric and not the curvature. Okay, I think I'll call it there.